Welcome to the practice questions on being able to find dy dx or f prime x in function form. What I'd like you to do now is to pause the video, have a go at questions 1, 2, 3 and 4, and then when you're happy with your answers, then restart the video, go through the model answers with me. So if you pause the video now, have a go at these 4 questions. Hi, welcome back. Let's go through these questions now together. So what we've got to do is we've got to differentiate these expressions. Differentiate means find dy dx. So if we're finding dy dx, you should know that, just write this up here, that if we've got y equals, for example, x to the n, then dy dx is going to equal n times x to the n minus 1. So that's what we're using on these expressions here. So we write down dy dx. I like to think of this as difference in y, difference in x. This is going to give us our gradient function. So what we do is take the 5 to the front, times it by x, and then reduce the power by 1. So this first one becomes 5x to the 4. This one here, well, this is going to be, if we think of this as 1 here, 1 times 6 is going to give us 6, so we have plus 6. And then if this 1 goes down to 0, this becomes x to the 0. Now x to the 0 is 1, so 6 times 1 is just 6. So basically the x there just disappears. And the 1 on the end there, that disappears totally. Because if you think, if we had a graph, and if you view the lesson, I'll go into this in more detail. If we've got our graph here of y equals x squared, then this part here just moves the graph up. So it's just going to move that graph up. If this was a minus 1, it would just move the graph down. Now by moving this graph up or moving it down by this value here, it's not going to change the gradient in any way. So this 1 does not need to be included in our gradient function. So it just disappears. So our answer becomes 5x to the 4 plus 6. Question 2 then. This one we've got some fractions in it, we've got some minuses in it here. So same procedure here, dy dx. And if we take the half and times it by the 5, well, that gives us 2.5, which we write as 5 over 2. Keep it as a fraction. So 5 over 2x. This power here goes down by 1, which takes us to negative 1/2. Then the second term here, 3 times 3, gives us a negative 9. And the power goes down by 1, so negative 9x squared. And the last one here, well, we've done the 6x already, we know that the x just disappears, so it becomes plus 6. Question 3. We've got this in its different form here. We've now got this function of x. So here we write this as f, the differentiated function is f dash x or f prime x. But the procedure is exactly the same. So here we take our power, times it by our coefficient, which gives us negative 6x, and the power reduces by 1, which goes to negative 3 because we're going down the number line. And then the 5x here, just the same as what we had over here with the 6x. The x just disappears, so we end up with minus 6x to the negative 3 minus 5. Now these terms could be written differently. You could write this, you could simplify this a little bit and write it as, we could have minus 6 over x to the 3 minus 5. And obviously if you need to start putting values into x, it's better to write it in this format than this format. And the last one here, question 4. So we've got f dash x to show we're differentiating. 4 times negative 7 gives us negative 28. Let's reduce the power by 1, goes to a cube, sorry, spell that out. So this one, power goes down by 1, 2, 3. And then the second term, negative 3 times 8, gives us negative 24. And if we reduce the power by 1, it goes down to negative 4. And of course, again, we could write this, keep that one as it is, we could write this as negative 24 over x to the 4, if you like. And that's better if you put in values of x into the expression afterwards.